Hello friends, today I will show you the Rubottom oxidation, and it's a very nice reaction, and this is a useful high yielding chemical reaction between Silyl enol ethers and peroxy acids to give the corresponding alpha hydroxy carbonyl product. So suppose you have this carbonyl compound here, so in alpha position, in this is the alpha position to this carbonyl group, alpha position. In this alpha position, if you want to put a hydroxyl group, so you can do it by making a TMS enol ether, like OTMS double bonded. You can do by using the LDA and then the quenching with the TMS chloride. So this is not the part of this Rubottom oxidation, but you need this TMS enol ether, and after that you can use mCPBA in DCM, and mCPBA is like meta-chloro-perbenzoic acid. Remember that there is one oxygen additional, that's why it is called perbenzoic acid. So M is meta position chloro, C means chloro perbenzoic acid in DCM. So you have to do this reaction like this, and after that if you use the TBAP, you will get the hydroxyl group in this position. So how it is happening, like what is the mechanism of the Rubottom oxidation? So I'm gonna show you. So here I have written the total mechanism of the Rubottom oxidation, and it is very interesting. So first, TMS enol ether react with the perbenzoic acid, metachloroperbenzoic acid, or mCPBA, and it will give you a byproduct like metachlorobenzoic acid that is not required for us. And during the workup of the reaction, we do like aqueous sodium bicarbonate solution extraction. So with that, this that carboxylic acid will be gone as a salt with the sodium, and ultimately your organic part will be formed as this, like double bond is captured, one oxygen for this perbenzoic acid, and it forms this siloxyoxyren. And this siloxyoxyren intermediate get the acid catalyzed ring opening. So first it get the proton, and that proton is abstracted by this oxygen, and ultimately this ring can be opened and it forms oxocarbenium ion, or so this is called oxocarbenium ion. There is a positive charge, and after that this lone pair of the electron will be donated to the silicon, and that bond with the oxygen silicon will go back to its original position, and this process is called 1,4 migration, Silyl migration, 1,4 Silyl migration. And this process is called like Brook rearrangement. And once this migration happens, then one proton will be removed, and ultimately you will get alpha siloxy. Like alpha siloxy means oxygen and silyl group, trimethyl silyl, so alpha siloxy and carbonyl derivative. So once you have these, like that original carbonyl group is back, and now you have to remove this silyl group. So you can use either the fluoride source as a TBAP, like tetrabutyl ammonium fluoride, or in some cases in presence of acid or base, this silyl group can be removed, deprotected, so that OH, you will get the OH group. So this whole process is called Rubottom oxidation. The original implementation of this Rubottom oxidation featured the peroxy acid metachloroperoxybenzoic acid as the oxidant in dichloromethane in the case of Hassner and Brook, and hexanes for Rubottom. Well, the reaction has been tweaked and modified since 1974, but still mCPBA is commonly used as the oxidant with slightly more variation in the solvent choice. In many cases, especially DCM is the most common solvent, but in some cases people also choose hydrocarbon solvents like pentane and toluene. It is to be noted the reaction proceeds at relatively low temperature and heating beyond room temperature is not necessary. Low temperature allow the standard Rubottom oxidation conditions to be suitable with a variety of sensitive functionalities, making it ideal for complex molecule synthesis. But in some cases, this reaction also may require a little bit warm up, like 0 degree or like 5 degrees Celsius, but it depends. Silyl enol ether substrates can be prepared regioselectively from ketones or aldehydes by employing thermodynamic or kinetic control to the enolization prior to trapping with the desired organosilicon source. You can use TMS chloride, that's what I was showing. You can use LDA to abstract the proton, make the double bond, and then quench the reaction with the TMS chloride. Then you can get this TMS enol ether. So Silyl enol ethers can be isolated prior to exposure to the reaction conditions, or the crude material can be immediately subjected to the oxidation without isolation. But if you can purify that Silyl enol ether is stable in your compound, then you can purify, like I purified my compound. So this reaction can be used by both acyclic and cyclic Silyl enol ether derivatives. So now I'm going to show you the reactions, how I am doing the reaction. Let's see. So to do the Rubottom oxidation, I dissolved the compound in DCM, and now it has a magnetic stirrer. Magnet is stuck, so I'm just dislodging the magnet from the flask. Then I will pull it down to the DO flask at minus 15 degrees Celsius, and then I'm going to add solid mCPBA under alcohol, and I continue the reaction at minus 15 to minus 12 degrees Celsius for 1 hour. And after 1 hour, I'm going to add same amount of the solvent, 1 gram, like 10 milliliter DCM. So if you have suppose 500 milligram, then you have to add 5 ml DCM. So here I have 700 milligram of the compound. So accordingly, I added the solvent, and after that, I will add the same amount of the solvent after 1 hour. So I'll show you how I'm doing the reactions. So I'm using acetone and dry ice. So you have to add not too much of the dry ice, just controlled way. Normally you can also do lithium chloride acetone, but to go to the minus 15. But sometimes if it is not available, then you can add the controlled way. But you have to keep an eye on that, like when it is. So now you can see this is around minus 15 or something. You can see that minus 15 below 0. And I'm using dry ice and acetone. So once mCPBA is added in the solution of the compound in DCM, so I put a paraffin with the rubber separator and the round bottom flask, and to evolve the extra build-up pressure in the flask, I connected to the argon line, and it will release in the gas. Also, I kept the argon gas on a little bit, so maybe I'll just close it down and maybe I'll put it at positive pressure, like very slow gas. So you'll see like just single drop. So it means it will keep this reaction under inert atmosphere. And now I'll continue this styrene for 1 hour, and definitely time to time I'll check the temperature as -15. Even if it goes increased to -12, it's fine, but not above -10. So if you see the thermometer, now it is around -17. So I'll keep eye for 1 hour. So after 1 hour, I will add more DCM, same amount of the DCM solvent, and then I will warm up to the room temperature, and I will start for 30 minutes. But now at -15 degrees Celsius, it will be like 1 hour this time. So after 1 hour at -15 to -12 degrees Celsius reaction, so I am taking 9 milliliter more DCM, while this DCM is under argon. So just this silk bottle, and I does DCM, so I will take this DCM. Addition is done, so you can remove the. Now you can warm up the reaction with the newly added solvent, and now I'm just removing the low temperature thermometer, and also how I'm going to remove the this whole reaction setup. So before removing, make sure that I'll take it out from this dual flask. Take this out, and now I will slowly put it down at room temperature, and it will be stirring for additional half an hour. Then I will quench the reaction. Okay, after 30 minutes, use saturated sodium bicarbonate and saturated sodium thiosulfate 50-50 mixture, and add in the flask. So basically, it will remove the excess or like produced byproduct metachlorobenzoic acid. So that will form the sodium salt and it will be in the aqueous form. So now you can extract your reaction. So this reaction is done. So I will just remove this gas part and I will stack it here so that I don't get the puncture. So I will insert it and then I will open the reaction mixture and I will pour everything. Remember, this solvent was DCM, so I'll pour everything in the separatory funnel and I will add maybe I'll extract. I will separate the DCM part first, like in a flask, and DCM is heavier than the water, so my product and DCM will be bottom of the separatory funnel, and then I would add additional DCM and shake it in the separatory funnel and separate it and get the DCM again separated. By this way, like I will do 3-4 times, and so that all organic part is with my DCM part, and then I will remove the DCM and I'll get the my crude product that would be your siloxy ketone stream. So now this part will give you so up to this, whatever I did, I got at least this part. Now it should be this trimethyl siloxy, whatever I have, doesn't matter. So basically it had this, so it was like double bonded here, and then with the mCPBA reaction it should form this thing, this, and then after the reaction is done with in presence of sodium bicarbonate and sodium thiosulfate, it should open and do the 1,4 migration here, so siloxy intermediate. Now I want to get hydroxyl group here, so once I get the crude, I'm going to use TBAF in THF at minus 5 degrees Celsius for 2 minutes, and then I'll quench the reaction with sodium bicarbonate, aqueous sodium bicarbonate solution, and then finally I should get this compound, the OH. So now I'm going to do the extraction, separation, and remove the solvent. And this is the reaction called Rubottom oxidation. So hopefully you can understand the Rubottom oxidation process, mechanism, and also how to do this reaction practically. Thank you for watching my video. See you in the next video. Bye now.